Welcome to the 2020 SIAM conference on the mathematics of data science. My name is Joel Trop. I'm one of the co-chairs along with Ali Pinar and Gita Kutinyak, who are also here in the audience with us. As you know, data science has made a tremendous impact on the world in recent years, and it's become an integral part of the Society for Industrial and Applied Mathematics. The Society has started a new journal on the mathematics of data science, and we're in the process of developing a new activity group on the mathematics of data science. You can see the enthusiasm for this subject in the number of speakers that we had lined up for the conference in Cincinnati. There were almost 1,000 people who were going to speak in the physical version of the conference. But as you know, there's been a little turmoil and we've moved the conference online. On behalf of SIAM, I'd like to extend my sympathies to all of the victims of the COVID-19 epidemic and also the epidemics of violence and racism that are going on right now and have been going on for a long time. I'd also like to thank all of the organizers of the meeting and everyone at SIAM for their support in bringing this conference to our community. Now, we've already held a number of mini symposia online and a mini tutorial. All of these are available online. You can see the program at the conference website where you can learn more about these things. This talk today will be available online in a live stream and also be archived. And this is the very first in a sequence of plenary talks by luminaries in the field of data science, which we're very proud to be able to offer and to support. I do have one announcement before we begin. Andrea Bertozzi's talk, which was scheduled for tomorrow morning, has been moved to Monday, June 22nd because of the scheduled protest, #ShutdownSTEM, and SIAM wants to support that activity. So Andrea will be speaking a little later this month. All right, with that preamble, I'm delighted to be able to welcome our first speaker, Mike Jordan, the P. Hung Chun Distinguished Professor at the University of California at Berkeley. As you know, Mike may be the most influential researcher in all of computer science. He has a long tradition of work in machine learning and AI, going back a few years. I'm not going to bore you with all of the long list of distinctions that he's received, but I will mention that he's a member of the National Academy of Science, the National Academy of Engineering, and the American Association of Arts and Sciences. Now, a little closer to home, Mike was one of the founding section editors of the SIAM Journal on the Mathematics of Data Science, and so he's really played an active role in promoting this activity within our community. And one of the things that I love about Mike's work is that he always emphasizes the importance of mathematics and rigor in the field of data science. Now, one last item, there will be a question and answer session at the end of the hour. If you have questions, please enter them into the Q&A facility here on Zoom, and the co-chair Gita Kutinyak will moderate the question and answer after Mike's talk. Anyway, thank you so much for your attention, and like the rest of you, I'm looking forward to hearing what Mike has to share. Thanks, Mike.
All right, thank you, Joel. So first of all, hello to everyone. I'm honored to be participating in this series. Thanks to Joel, Gita, and Ali for inviting me, and honored to be connected to all of you wherever you are. I have started to enjoy these presentation styles because I know that I'm connected throughout the world, and especially in this era, that's comforting to me. So I'm going to jump in. I have a lot to say. I have a bit of a story to tell that has got several pieces to it. The first piece is a bit philosophical. I want to say something about machine learning, because I think after 30 years, I finally realized what it is. And I'll say kind of how that relates to data science. I think what we're seeing in this era, and we have been seeing, is the emergence of a new engineering field. And I think of that historically by reference to previous emergences of engineering fields. So think about chemical engineering. In the 20s and 30s, there was no chemical engineering. There was chemistry, there was fluid flow, and there was the ability to make chemicals in the lab in small quantities. People perceived at that point it was possible to create vast systems that created chemicals at vast scale called factories. And it was hard. So they started to build these factories, and sometimes they worked and sometimes they didn't. And whole new principles had to be developed to build these things at scale. So new kinds of thermodynamic laws, new rules of fluid flow at scale, and so on and so forth. That had to be economically viable and safe, and so on and so forth. So a new field emerged. It was called chemical engineering. And it wasn't just engineering, quote unquote. It was mathematical. There are mathematical ideas and principles and new theorems and so on and so forth in chemical engineering. You know, same thing happened in electrical engineering. Before it emerged, there was electricity, there was electromagnetism, there were Maxwell's equations. So in some sense, you were done. But no, you had to figure out, you know, notions of like impedance and how do you build circuits and how do you bring electricity across a country and so on and so forth. That got called electrical engineering. And it was, again, highly mathematical and full of theory and so on. And, you know, civil engineering likewise. So I think what's emerging now is an engineering field that is based on data, fundamentally. It's based on people and people's preferences, and it's based on planetary scale webs that connect all of this. All right, so that's worthy of a new engineering field. It is the attempt to build systems that work and are safe and are interesting and make people's lives better, just like the previous areas of engineering. All right, so I think that's what machine learning actually is, or it was in the early 80s when the term started to get to be used. There already existed statistics, there was inference, there was decision making, and it was kind of put together and with optimization and so on, kind of into a new problem solving tool to solve real world engineering style problems. And for better or for worse, the statisticians hadn't really aimed at doing that. Statistics was kind of in service of science, at least in its recent incarnations. So there was this opening here, and it was filled. I think data science is very much in the same spirit. It's broader. So I think of it as including database people, for example, who weren't included in machine learning. And it is often in service of science, a little bit more than machine learning has been per se. But I still think it's kind of facing some of the external planetary scale issues in data flows and decision making. And that is a new engineering field. It's going to take decades to have this field roll out, by the way. It's a really complicated field. The challenges are vast. They do involve people, and they involve, you know, think about the medical system or the transportation system or something. That's the scale that we're talking about. And principles to make those systems scale, be robust, work, be safe, and so on, are still yet to emerge. All right, so if this is a correct perception of the world, there should be some history, and here's my history on this first slide. So this is the history of, let's call it machine learning now, not as the algorithmic history or the architecture or the academic history. This is the real world history. So already in the early 1990s, there were Amazon and other companies that were building vast server farms with algorithms, mostly random forests in the day, to do things like fraud detection and supply chain management at scale, with large numbers of computers and huge data sets, and with a real interesting business model. And they solved a lot of those problems, at least at the scale of the time. You know, and Amazon is now able to bring 1 billion products to hundreds of millions of people within a day or two. And you can imagine behind that is a system and data. Still, the principles have to yet emerge. But so the second generation to me was realizing that a lot of the data was about humans and about preferences. And so there started to go a little bit more towards utilities and economic story, and recommendation systems emerged in that era. It's a $1 billion industry, and as was the first generation. So this was real, and many more companies started to have business models based on data analysis at scale. I think of our third generation now, with all the focus on neural nets and deep learning, as a pattern recognition era. So it's all about finding patterns. It's Dude and Hart on steroids. And the focus has now become things like speech recognition, computer vision, and forms of natural language translation. And since it looks human-like, people have want to call this for better or worse. So I think it's great. There's nothing wrong with it, but pattern recognition is limited. That is not the whole problem of building large-scale planetary systems that deal with data. There's the decision side, and there's the markets side. How do you put all these decisions together at scale so they don't conflict, they find coalitions where possible, and they trade off various decision-making outcomes. So I'm going to argue there's a huge new set of challenges. Indeed, as Joe alluded to, mathematical challenges emerging now as we put together microeconomics with statistics and computation in new ways. Here's some of the problems I've been working on the last 10 years that have this flavor. I don't want to get into this slide, but just to kind of briefly allude to a couple of them. Systems that create learning-based markets. So there's three words there: systems and learning and markets, that usually are not put together. And I think that's the critical challenge, is to put them together in interesting ways. Multiple decisions, where statisticians have had a lot to say. Many people outside statistics aren't aware of false discovery rate ideas and multiple decision-making issues. They will continue to expand. They're very, very important. And then many others, including things like, real uncertainty, cloud edge interactions, abstractions, provenance. These are all kind of, how do you support your decision-making? How do you make sure that it's not stale data the decision is based on, and so on and so forth. So there's a blend of computer science and statistics and mathematics throughout this slide. There's not a lot of what's the theory of deep learning here. I do think that's important, and the pattern recognition thing is not done. But I think that there's been way too much focus on solely that and not thinking about the other issues that really emerge when you build real world systems. So let's just dig into this for a moment, just kind of a almost thought experiment. Let's think about, you walked into a doctor's office tomorrow and the doctor measured all kinds of things about your body, including your genome. And so maybe a 50,000 dimensional feature vector went into some large neural net, and the neural net's been trained on all the world's medical data. So the biggest, best neural net ever built. And so it's supposed to predict what kind of diseases you're about ready to have. And it's supposed that if one of the outputs is over 0.7, you're being predicted to have liver problems. Maybe you should consider a liver transplant. And suppose the number is for you 0.701. Is that thresholding a decision? Well, and no. You're going to first of all ask, what's the error bar? And error bar itself is a complicated notion. Error bar means uncertainty, but where's the uncertainty coming from? Is it that you used data that's not quite relevant to me? Was the data out of date? Was it, was a different machine used? Was a sampling pattern not quite right? All those contribute to a notion of an error bar. And I need to know that if I'm going to make an actual decision. All right, but it's not only that. When we have real consequences, you're going to think about counterfactuals. What if I exercised more? Did you know this about my diet? Did you know this about my family history? And so on and so forth. And pretty quickly, you're going to realize that neural net did not have all the world's knowledge in it. There's lots it missed about me in my moment and in my history and so on, obviously. And so I'm going to add that now to the story, and we're going to have a little dialogue. And so an actual doctor would probably rerun an analysis in their head based on the new data. So we have to have a whole system around even just one decision that involves things like provenance, relevance, and counterfactuals. But it's never just one decision. Think about the medical decisions right now in the COVID episode. These are linked around the planet. If you try out a treatment somewhere, that affects someone else's treatment within a matter of hopefully hours or even minutes. It's been done very ad hoc way right now, but it really is sets of decisions across a network. And of course, it's sets of decisions across a network over time. And this is all done asynchronously. And so we got to worry about double counting issues. We got to worry about, again, provenance issues and so on and so forth. All right, but it's even more than that. It's decisions where there is scarcity and competition. All right, if we're talking about decisions in the virtual world, there's really no scarcity and competition. We can copy things as many times as we want, but in the real world, there's always scarcity and competition. So I can't make my decisions alone. I've got to make them aware of the other decision makers and what they're trying to do. And I have to bring in a microeconomic perspective. All right, so here's again a thought experiment that at least helped me as I started to think about these issues a few years ago. It's just to think about a classical recommendation system. It's just a pattern recognition system. It finds patterns in data, and it will sort of do some decision making. It'll recommend purchases to you based on similar customers from similar customers. But if you now put in the real world component, you think about the competition. What if I recommend this movie to a lot of people, which is certainly what happens at Netflix or Amazon? It's not a problem because in the everyone, I've got to now worry a little bit more. I got to do print on demand, but still there's not a lot of scarcity. If I recommend the same restaurant to everyone, I got a problem. Okay. The problem is that, too many people will go there and I have to do some kind of load balancing. And I don't want, as an algorithm designer, to figure out how to do that load balancing. I don't really know which restaurant you really want to go to in that moment. In fact, you don't know. Similarly, what street should you go down to get to the airport quickly? There is a fastest path, but if everyone's taking it, we create congestion. So who do I put on the fastest path and who do I put on the slowest path? I've got to create some notion of an economy here. I got to create a bidding system or some kind of an auctioning system of some kind so that I start to raise economic value and I don't just make ad hoc decisions. All right, now I'm doing this in the microeconomic context, but where I don't know the preferences a priori, because no one really knows how fast they are in that particular moment until you ask them. All right, so the alternative to this kind of CS machine learning way of thinking of I'm going to build the world's best system and it knows everything is to create a system that allows people to make decisions on the fly based on evolving preferences and decisions of other people. So we want to create multi-way markets, maybe diners on one side of the market and restaurants on the other, and they make bids to each other based on recommendation systems of their previous experiences. So they're learning their preferences. I don't know a priori which restaurants I like in Shanghai, but as I start to have experiences, I do like a bandit algorithm. I start to prefer certain ones. I want to go there, but Joel also wants to go there, and there's a bit of a competition. So we've got to have our bandit algorithms will be aware of each other. There's new mathematics that's needed here to think about things like competing bandit algorithms in a microeconomic context. All right, so let me just say this one more time. So markets can be viewed as decentralized algorithms. They are algorithms. This is not new to me. People have said this in the past. They accomplish complex tasks like bringing the goods in and out of a city every day, rain or shine for thousands of years at different scales and so on and so forth. So they're adaptive, robust, scalable, and so on. These are a lot of the goals of current AI. And people talk about that as if it's just pattern recognition and getting the right data sets. Well, no, it's much more than that. And it should incorporate microeconomic principles. You already get a lot of these things, not for free, but you get them as part of market principles without having the learning system have to do all of them. Now, of course, markets aren't perfect. They have many problems. A lot of those are worked on in economics, but a lot of them haven't emerged yet because we've never really tried large-scale learning-based markets. Here's some of the things that I'm currently working on, just to give a little flavor. Markets in which individual agents have to explore to learn their preferences. We're bringing in bandit-style exploration, recommendation systems blended with markets, and so on and so forth, okay? So I'm going to get into a couple of examples of this near the end of the talk to give a flavor of where I'm at right now and what kind of things I think are possible and show you some actual theorems. All right, but as I get towards that, I'm going to now sort of shift gears a little bit and sort of talk about what is going to be the mathematical interface between machine learning or statistics or whatever you want to call it and microeconomics, whatever you want to call that. Okay, so there has been, paths across these things. There's like the algorithmic game theory links these things to some extent with not so much learning. There's, Hamilton-Jacobi-Bellman equations that, sort of encompass all of this at some level. But there's new mathematics needed. And so for me, the interface is dynamical systems, optimization, stochastic processes, the kind of things that we've gotten really good at in machine learning and statistics in the last few years and not that many people are aware of. So I'm going to tell you a little bit more about our progress there, because I think that sets the stage now for new context to be made to microeconomics. I should say I'm not a microeconomics person, but I'm learning quickly, as quickly as I can with books next to my bed. Just one perspective I have currently, and I think a lot of economists share this, the future is going to be all about the dynamics. Economics is rarely going to be at equilibria. Things shift, people learn, things adjust, the world is changing. So the classical equilibria, Nash, et cetera, and Stackelberg are not going to actually be the focus here. It's all going to be about the dynamics as you move around certain sorts of topologies and certain sorts of geometries and stochastics. All right, so with that in hand, I'm going to tell you a little bit about some of the things that have helped condition me to what new things I think we can do in microeconomics, because we know some things about geometry and dynamical systems. I'm going to review a little bit of work from the last few years, trying to tell a story, and then get at the end to come at some actual microeconomic examples. So here's a paper I want to highlight with Chi Jin and other colleagues, Praneeth, Rong, and Sham, from a few years ago that really helped me. This is about non-convex optimization. And it's going to be some mathematics about that, particularly focused on dimension dependence, not just rates. It's actual thinking about the space we live in and the geometry effectively. Sort of bring dynamics together with geometry. All right, so you all know what a saddle point looks like. In 3 dimensions, it looks something like that, but we want to think about hundreds or thousands or millions of dimensions and the saddle point could be arbitrarily oriented. And if we're a gradient-based algorithm, we'd sort of sniff it out as we move towards it, but we have no idea which are the directions that lead us out of the saddle point and how to find them quickly, and so on and so forth. All right, so we might naively expect that these are going to be really troublesome, that there'll be exponential dependence in dimension as we have to do some kind of a search process to figure out the way out of a saddle point. Now, we know empirically that gradient-based methods seem to work in problems, not just neural nets, but other ones where there's lots of saddle points, including various kinds of mixture kinds of problems. So maybe it's not exponential, but we now need to do the math to figure this out. So just a little bit of background here. It's known that gradient descent asymptotically will avoid saddle points. So in continuous time, this is a fact about gradient flow. It's been known for a long time. It's basically out of Morse theory. We had a paper doing this with actual gradient descent and similar kind of result. So you think of that as a positive result in the old days, but nowadays we don't think of that as positive. Asymptotics is too long. And in fact, we know that it can take exponential time to escape saddle points. So even though you'll eventually escape them, gradient-based methods can get stuck for a long time. At the same time, we had a positive result already back in 2015 by Gu et al., proving that if you add a bit of stochasticity, you can escape saddle points at polynomial time. Okay, polynomial in the dimensionality. We're starting to get at dimensionality here. All right, but polynomial could be, d to the 45th, or even d to the third wouldn't be any good when d is hundreds of thousands or millions. So can we prove a stronger theorem? That's what we aimed at. So just to remind you of Yuri Nesterov style theory, let's look at convex optimization. Here's gradient descent. And as hopefully you all know, this thing will converge in the convex case to a global minimum, but maybe less known, very important, is the number of iterations to arrive at the global minimum within an epsilon ball is independent of the dimensionality. All right, that's already a striking fact about gradient methods. You can run them in infinite dimensions and they take as many steps as they do in finite dimensions. Really amazing fact about the gradient method. All right, and here's a little mathematical setup. If we're in the Lipschitz case and we want to arrive within epsilon of some stationary point, if we do that for all epsilon, we get a rate, and there's an example of a classical rate. To arrive within an epsilon ball, it takes you 1 over epsilon squared iterations. There's a 2, there's a Lipschitz constant, and there's the initial distance from the optimum. So this is a beautiful theorem. There's no hidden constants. It's not asymptotic. It's all sitting there. These are natural constants. It's kind of, you solve the problem. All right. And you notice that there's no dimension dependence. No D is sitting there at all. So that's a beautiful fact. Now this is convergence to a first order stationary point. Gradient is small. What if you run gradient descent on this surface? Well, it'll move, but it could hit a saddle point for an awfully long time. It could even hit a local maximum and so on. So what do we know about that? All right, so let's add a little more structure. Let's give ourselves a little more smoothness. Let's have a Hessian that doesn't vary too much. And now let's ask not to hit a first order stationary point, because that could be a saddle point. That's no good. We want to hit a second order stationary point, i.e. we want the gradient to be small, and we want the minimum eigenvalue of the Hessian to be greater than or equal to 0. And again, we give ourselves a little ball around that. And that's parameterized with a strange parameterization, that square root of rho epsilon, just so we don't introduce any new constants in the problem. We got the Lipschitz constant and the same epsilon as before. So we've analyzed in that first paper, at least, just a very simple perturbation of gradient descent. We know we need some stochasticity. So we did it by adding uniform noise from time to time in a ball around the current iterate. And we did it sporadically and only once every capital T steps, where we know how to tell you how to set capital T. All right, with that setup, we got a theorem. Here it is. To find a second order stationary point in the non-convex setting, the number of iterations again goes as 1 over epsilon squared. So no loss relative to gradient descent. That's striking. We can do non-convex optimization with no loss in terms of that rate. But what about dimension dependence? Well, we have the Lipschitz constant, initial distance, it's all looking the same except that little tilde. And that's where we traditionally hide dimension dependence, because we can't figure it out. But we did figure it out, and the dimension dependence is logarithm of d to the 4th power, so polylogarithmic in d. So it's not exponential, it's not polynomial, it's actually all the way down to logarithm. Now, I don't actually believe that 4. That's probably the proof technique, but even after now 3 years have gone by, we don't know how to get that thing down all the way to logarithm, which I think is what it really is. All right, nonetheless, the point is it's really hardly dependent on dimension. And this really suggests why these stochastic forms of gradient descent can work in these non-convex problems. It's one of the ingredients of the explanation, which is that they don't take a large amount of time to find the directions out of the saddle points. Now, our proof technique is what I wanted to emphasize here, actually. Effectively, this is some differential geometry, but it's hard differential geometry in hundreds of thousands of dimensions. So we did probability theory instead. All right, and so here around a saddle point, there's going to be a region, that green region, where the flow is mostly towards the saddle point. All right, outside the green region, you see the negative eigenvalue and you move out exponentially quickly. All right, so the real question is, how thick is that green region? All right, and the way we figured that out, upper bounded it, was by starting by a coupling argument. You start two diffusions a distance little r apart. If they're really close to each other, r is small, both of the diffusions will be in the green region and they will both flow towards the saddle point, and they'll probably couple quickly. At some point, as r gets larger, there'll be a phase transition where one of them is outside the green region and flies apart and they never couple. So you look for a phase transition in the coupling time of coupled Brownian motions. And with that, we're able to get this logarithmic dependence. So that kind of coupling argument we've used again and again and again in a whole raft of other papers after this. The coupling arguments, and it's not just one kind, there's many different kinds, allow you to do geometry, differential geometry, while avoiding the geometry. They allow you to capture the geometry with probability theory. And that's been really helpful to get these high dimensional results. All right, once you get a result of that kind where there's no hidden constants and you maybe even nail the dimension dependence and the rate and so on and so forth, you think you're kind of maybe done. And you know you're done when you can match with lower bounds. All right, so the second set of ideas we developed along the way here, which again, I think are going to be useful going forward, are kind of more of a constructive way to get lower bounds and to get rate matching lower bounds. I do want to point out a paper I forgot to put in the talk, but is on my website. You'll see a very recent paper with Michael Muhlebach where we have continuous time lower bounds. And that's been an open problem of how to find lower bounds in continuous time. I want to highlight that paper on my website with Michael Muhlebach. All right, so lower bounds due to Nemirovsky and Uden allows you to focus on the inessential, get rid of the inessential parts of the problem. And actual algorithms that meet lower bounds are often called accelerated algorithms, and Nesterov was the leader in developing these. Our perspective on this, and not just ours, but a number of others, is that it's essential to go to continuous time to understand these matching of upper and lower bounds. In discrete time, where most of optimization theory and computer science, for that matter, have stayed when you talk about dynamics, it's not really clear what you mean to accelerate. If you're hopping along a set of points, what does it mean to hop faster? You really need a continuum to embed the notion of acceleration in. And if you're going to ask questions like about what's the fastest you can go, again, being in discrete time, it seems a little hard to even formulate that problem. All right, so this was a line of work on variational Hamiltonian symplectic perspectives. Again, I'm going to go somewhat quickly. I just want to allude to some of our key concepts here. Really going to continuous time into physics kind of concepts was really essential, both to get constructive methods meeting lower bounds and also understand the upper bounds better. So Andrea Wibisono and Aisha Wilson were key in this. Their work, they did their thesis at Berkeley in developing aspects of this. Aisha in particular developed the Lyapunov arguments that were critical for us to get a lot of these rates. And then Mike Betancourt helped us with some of the early symplectic work. So let me go again back to Nesterov and others. Unconstrained convex optimization. Here's gradient descent again. Another way of expressing the rate is that after k steps have gone by, you're within a ball of size 1 over k of the optimum. At some point, somebody, probably Nemirovsky, asked, is this the best you can do? Ask a complexity theory question. What does that mean? Well, you now got to talk about a machine to talk about the best you can do. And so Nemirovsky and others thought about a machine that could look at gradients and keep memory of all previous gradients and make movement in the span of all the gradients you've seen so far. That's an example of a machine. It's not Turing complete, but it's a powerful machine. It can do conjugate gradient and so on. In that machine, how fast can you go if you've got an unconstrained convex, smooth convex optimization problem? And Nemirovsky and others found a lower bound of 1 over k squared, faster than gradient descent. And it was, I think, to people's astonishment, that an algorithm existed and was discovered by Nesterov that achieved that rate of 1 over k squared. And it was not just one gradient, it was two steps algorithm. It was a second order dynamical system. The first step was to do a gradient, and the second step was to do a little bit of a rotation, if you will, of the last two gradients. All right, so a very interesting algorithm, but the key was that it was possible to prove that this had the fast rate. All right, so where did this algorithm come from, other than out of the fertile mind of Yuri Nesterov? Is there a principle that delivered this algorithm and could deliver other algorithms like this for other manifolds, other geometries, other situations, and so on and so forth? So I think a lot of insight has come in recent years by going to continuous time perspectives on this problem. So first of all, just remember that gradient descent is the discretization of gradient flow, which is a differential equation, widely studied in mathematics. And moreover, gradient flow has a rate. For convex problems, if f is convex, the rate is 1 over t, smooth convex. So that corresponds to the 1 over k in discrete time. You can now ask, if we take Nesterov's algorithm, the two pieces, and take the step size to 0, you will get out a differential equation clearly. What differential equation? And this was done by Weiji Su, Boyd and Candice, 2014. And here's the differential equation that pops out from Nesterov. It's second order, obviously. There were two equations. It has a damping, and it has a mysterious 3 sitting there. And so there you go. So you can't solve this, but you can analyze it with Bessel functions and so on, and get some insights into the oscillatory behavior of this equation. So with Andre and Aisha, we looked at this equation and pondered it and asked, is there an underlying principle? Something like, maybe Lagrange looked at, F equals ma, a differential equation, said, what's the underlying principle that delivers that? Why is that a special differential equation? Are there any symmetries, et cetera, et cetera? So is there a variational point of view on this? In other words, this is a dynamical system which is meant to do optimization. Is there an optimal way to optimize? Is there an optimal differential equation? Okay, that's the question. All right, so we found a Lagrangian for this class of problems, a optimal way to optimize. And I'm not going to get into this slide. Again, this is a bit of kind of review, if you will, or just stage setting. But briefly, here's our Lagrangian. It's time varying. The alphas, betas, and gammas are not really important. They're different. They're sort of degrees of freedom to give us not just one algorithm, but a space of algorithms. They're just diffeomorphisms in time. The important part is that Bregman divergence, d sub h there. So you need an auxiliary function h, and you measure Bregman divergence between x, where you currently are, and x plus a time-scaled x dot. So it's a bit of an elasticity in the direction of motion. And you subtract off the potential. So it looks like a Lagrangian. And in fact, if h is quadratic, this reduces to 1/2 x dot squared minus f all time scaled. So it's literally a classical Lagrangian, but time varying. What do you do with Lagrangians? You put them inside a calculus of variations. You try to optimize over paths. You get out Euler-Lagrange equations. And that leads to, if you hit that with our Lagrangian, you get out the master equation there at the bottom of the slide, which is a second order differential equation, which is appropriate for a range of optimization problems. You can have different geometries in here and a range of different styles of problems given by the alphas, betas, and gammas. If you put in alpha is equal to logarithm of t, and you set beta in a corresponding way, and h is quadratic, this reduces to the Su, Boyd, and Candice problem that makes a continuous version out of Nesterov. So it has Nesterov inside of it, but it has a whole range of other accelerated algorithms. And in fact, we were able to get a rate for this equation once and for all. That was Aisha's work. We have a Lyapunov function that shows you the rate once and for all. The kind of interesting thing is that that rate in continuous time can be as fast as you want. Okay, so this is odd. Let's suppose I decide I want a rate of 1 over t, and I plug it into this Euler-Lagrange equation. What'll happen is I'll get out a differential equation. I can solve it. In principle, there will be a path in the phase space I'll follow, maybe that solid path up there. All right, and I'll move along it at a speed 1 over t. Now, suppose Joel comes along and says, no, I want to move faster. I know you can move to 1 over t squared. So I'm going to plug 1 over t squared in for alpha of t, a logarithm of that. He'll get out a different differential equation. He will solve it, and it'll turn out he'll move at speed 1 over t squared. But amazingly, he will move along exactly the same path I move along in this phase space. Okay, there seems to be some mathematical structure here. And now let's suppose that Ali says, no, I'm going to come along, I want to beat these guys, I'm going to move exponentially fast. So he sets alpha not to logarithm, he just sets it equal to t. All right, and he'll get out a different differential equation, and he will move along exactly the same path that Joel and I moved on. He'll just zip along at exponential speed. In continuous time, that's actually possible. You can go as fast as you want. So we've lost the phenomenon somehow, but we didn't, because we found out that this path is the critical part. The path captures the geometry and allows us to accelerate as quickly as possible. And speed is not important. It's like Einstein said, it's just the clock you're using. It doesn't matter, okay? Ali's just using a different clock, the diffeomorphism on ours. That's not important. All right, so we did actually discover something by going to continuous time. We discovered a characterization of the best path to follow, i.e. the geometry, okay? Right now, but when we go back to discrete time, something must break. And in fact, something breaks. Joel and I will be able to take our differential equations and discretize them. All right, we got to be careful. If we discretize them in stupid ways, we'll lose the fast rate. But I'm going to tell you there's a way to do that systematically. All right, and I'll still have the 1 over k rate from my 1 over t. Joel will have 1 over k squared. He'll recover Nesterov. And Ali will not be able to discretize his differential equation, provably, okay, stably. All right, so there is a phase transition in the ability to discretize certain classes of differential equations. That's actually a good part of what the acceleration phenomenon is about. And you would have not seen that unless you went into continuous time. The whole phenomenon is sitting there in continuous time. All right, so I view these as mysteries. Why can we not discretize when we're using exponentially fast clocks? What happens when we discretize and so on? All right, at some point, I remembered some lectures I'd attended back at MIT as a young faculty member on symplectic geometries and symplectic integrators. These are integrators that think about a vector field in a different way. So this is due to Hamilton, Jacobi, Poincaré, and others 100 years ago. And they were trying to discretize differential equations, you know, Newton's law, you know, Maxwell's equations, and so on. And instead of thinking about, I'm in a space, there's a vector at that space, I follow that vector a little distance, and then I go to the next vector and I chain along. I think about, I'm in a space and I have a little triple of vectors at a certain point. That defines a little volume element. And as I move along with the dynamics, I flow along, I want that volume element to keep constant volume. It's going to shear, but have it keep constant volume, right? And if I do that, I'm not only respecting the dynamics, I'm also respecting the laws of physics, conservation of momentum and conservation of other, you know, first integrals. So they've figured this out. That's called symplectic integration. It's highly stable because you're kind of keeping volume elements constant. And that means you can take bigger step sizes. And that's actually the connection to acceleration. Symplectic geometry allows you to characterize how big of a step size you can take in these kind of very fast dynamics situations. So here we are symplectically integrating a Bregman. Now we're in the Hamiltonian world instead of Lagrangian. That's just a Legendre transform, no big deal there. And you can see this thing is going down at the kind of desired rate, the oracle rate, and it's oscillating and it's super stable. If we compare this to Nesterov, this is on a different problem. These are all quadratic problems in high dimensions. It's just as fast as Nesterov. But it's actually even faster, because if I now turn up the step size for both of these algorithms, everything will shift over to the left, bang, Nesterov goes unstable and the symplectic method is staying stable. All right, so these are good ways to discretize these kind of differential equations. They had reasons in classical physics literature, but they also have reasons. They're a good way to think about optimization. All right, so that's a couple of years ago. We had an empirical paper with Mike Betancourt on this, but we didn't have a theory of if and only if kind of theory that symplectic integrators keep the fast rates. All right, and I'm going to allude to a recent line of work with Guy Franca and René Vidal. I'm going to skip this other part right here. I don't have time for it. This is a paper that we put out about a month ago where there is a theory of symplectic integration for dissipative systems. And there's several slides here I'm going to kind of just hop through. It's for those of you who know about Hamiltonians and symplectic geometry. I think you'll be interested to hear about this connection, the paper exists. So I want to just kind of highlight it here by showing some details, but not getting into the details. So let me just say what the problem is here. This theory that I alluded to, was developed by Hamilton and others, and they were interested in conservative systems. So systems that oscillate. In optimization, we're not interested in conservative systems, really. We're interested in systems that dissipate, that go to an optimum and stop. They don't oscillate, all right? So somehow there's a mismatch in the goals here. On the other hand, we found this symplectic idea allowed us to move quickly. So, we did get something out of it, but it was not quite the perfect match. So what we really need to do is think about how to think about dissipative ideas in the context of symplectic integration. And that's what this paper has done. Again, I'm just going to skip details here. I don't want to go through these slides. They're available. But we've got a dissipative system now where we have time dependence in the Hamiltonian. And we're going to ask about discretizations that preserve the stability of dissipative Hamiltonian systems. All right. So conservative systems are ubiquitous. All we want to do is put time dependence in our Hamiltonian, still have a theory of integration. All right. So we're going to do this with symplectic geometry together with backward error analysis. So that's a critical part. We want to do a theory here that allows us to do the error analysis because that'll give us these rates. Otherwise, this would be just stability results. And here again, it's a slide I won't go through, but just to say, you can pick up Herrer et al., vast tomes on backward error analysis for dynamical systems, and they're able to get rates, by doing interesting forms of backward error analysis on the flow maps of dynamical systems. So again, not going to go through details here. Just to say that this theory, very classical in applied mathematics, and is ready to be used for people like us. And so you do this, the geometry comes in by talking about symplectic manifolds, and all they are even dimensional manifolds that have these non-degenerate two forms on them. So things like momentum kind of quantities are captured by these two forms. These are symplectic, kind of having an anti-symmetry property. Okay, so that's very classical. It allows you to kind of put together this beautiful theory that emerged over 100 years of symplectic manifolds to go together with Hamiltonian systems, to go together with this particular form of integration, and it all just is a beautiful bundle of ideas. All right, but it's sort of only going to be relevant to us if we can do this for dissipative systems. All right, so now, first of all, what do you mean to preserve structure in this world? Well, it's Lie derivatives and brackets and so on and so forth. So it's a bunch of differential geometry ideas. And symplectic integrators are just things that have got these nice little invariance properties expressed in this mathematical language. Okay, and so you put it all together and you're able to analyze a discrete system in terms of a continuous system and a bounded error. So all the mathematics goes in, at the end of the day, from a numerical point of view, into this equation here due to people like Benetton and Giorgili. All right, what if we go to the dissipative case? All right, well, in some sense, that theory doesn't help you, at least directly. All right, but what you can do is talk about a pre-symplectic manifold. All right, it's a bigger manifold. All right. A picture is going to kind of summarize it here. We want to be on this blue manifold, that's the dissipative one, and we're going to embed this in a bigger lifted manifold, which is going to be a symplectic manifold, okay? And we're going to do a particular reduction between these two spaces, which is a form of gauge fixing, getting rid of spurious degrees of freedom in a dynamically sensible way. All right, so again, if you know some of these things, this will probably be familiar. Otherwise, hopefully this is just kind of mathematical cartoons for you. Okay, so long story short, in this paper, what we do is that we use symplectic ideas on a pre-symplectic manifold in which our overall problem is expressed using symplectic ideas. And that allows us to translate symplectic ideas into rates and backward error analysis for dissipative Hamiltonian systems, right? So at the end of the day, there's a theorem which says that you can have a numerical rate as expressed as a continuous rate with a bounded error. All right, and so just at the top of this slide, we've now applied this to a general class of Hamiltonians, which are time varying, and they have a separable form here involving kind of a kinetic energy and a potential energy kind of term, as in regular Hamiltonians. And in that paper, we show how to do this for the Bregman Hamiltonian, which I alluded to earlier, the Hamiltonian version of Bregman, okay? At the end of the day, here's the last slide on this material. You're able to start with one of these general Bregman Hamiltonians, and you're able to symplectify, and you're able to find some numerical maps that you put into your MATLAB or your Python or whatever, This is a particular string composition of maps that gives you a symplectic integrator. And this thing provably has the fast rate in discrete time that you had discovered in continuous time. Okay, so that was a bit fast, but anyway, I wanted you to be aware that these ideas exist, and I think it's real progress. I think it really allows us to put together dynamical systems, machine learning, geometry, and optimization. All right, so my last, I think, 5 minutes, Joel can confirm that, is to now, let's go back to microeconomics perspectives. I think now the open problems have to do with taking these perspectives and bringing them into new classes of problems. So one of the things we're going to want to do in microeconomics is talk about moving around spaces that have saddle points in them, because classically those had game theoretic meaning, things like Nash equilibria. In game theory, we're not trying to avoid the saddle points, we're trying to arrive at the saddle points. They have game theoretic meaning. Now we may not completely arrive there, we may just, what we want to define the dynamics that moves us towards these things at least. All right, so this has been a subject of a lot of work of, can I find Nash equilibria with gradient methods? And it turns out the answers have been mixed. It's harder. It's just naive gradient ascent descent will have limit cycles, and it will not even converge. So with Eric Mazumdar's a student here, Eric has led the work on us applying dynamical systems, and in particular symplectic ideas, to game theory. And again, with want of time, I just want to highlight a couple of points here. This paper exists, you can read. Just a little setup here. We're trying to do a zero-sum game in this particular case. Our work is not restricted to that, but we have a function f, and we have the negative of it from the point of view of the two agents. We have a gradient, and we have a Jacobian. If you do simultaneous gradient ascent, you can converge to limit cycles, and moreover, even more interestingly, you can converge to non-Nashed fixed points. And that's kind of obvious that if you take a saddle point, which is axis parallel, that's a Nash equilibrium. In one direction, you're happy if you go up, the other direction, you're happy if you go down. If you tilt that saddle point, it's still a saddle point, and gradient methods are still happy to find it, but it's not a Nash equilibrium anymore because neither agent is happy. And just topologically, if you have a bunch of Nash equilibria around your space, you're going to have a bunch of tilted saddle points too. And this is the kind of thing that gradient algorithms find, and they're spurious. They're a problem. All right. So long story short, if you run even some of the more sophisticated algorithms that avoid limit cycles, they will unfortunately hit these non-Nash equilibria. So here's a bunch of different algorithms that have been proposed recently. The blue star in the middle there is a non-Nash equilibrium. It's a saddle point which is tilted. These algorithms also hit the green crosses. Those are Nash equilibria. That's good. But they unfortunately hit the blue star, which is a tilted saddle point. All we did is we took the symplectic component of this gradient field, right? And we, instead of highlighting it, it was like we did in the accelerated algorithms, we removed it. The symplectic component turns out to be the component which is responsible for the oscillations. If you remove it, you provably get rid of the oscillations. Moreover, you provably get rid of these non-Nash equilibria. So over on the right there, you'll see this algorithm, the little red dashed line. It heads towards the non-Nash equilibrium, the tilted saddle point, but it sniffs out when it's in the neighborhood that it's no good, and it moves away from it and hits a Nash equilibrium. So that's pretty interesting dynamics. And there's a lot to explore here about things like rates and so on and so forth. I just wanted to highlight that symplectic geometry was being used now in a surprising way in the game theoretic setting. All right, and last but not least, so that was kind of a long dash through dynamical systems and all leading up to some game theory. This last little project I want to mention is kind of more reflecting where I hope to go in the future. So as I alluded to earlier, I want to do things like bring bandit algorithms where you have exploration, exploitation, and rates and so on, regrets, in contact with things like matching markets for microeconomics, a form of game theory. So this is work with Lydia Liu and Horia Mania here at Berkeley, students in my group. And just briefly, multi-arm bandits are my favorite learning problem, more favorite than supervised learning, because they have the core of the learning problem. You're not being told the answer, you have to figure it out. All right, so you're trying to figure out what's the highest reward that I can get out of a number of different choices. So I get rewards by picking them. There's a well-known, beautiful algorithm that doesn't just return the mean reward I've seen so far, but returns a confidence bound on the reward. And I pick the arm that has the highest confidence bound. So that both makes me pick good arms, but it also picks the arms that haven't been explored very much yet. And so it has two ideas embodied in one. So as I move around and pick the arm with the upper confidence bound, I have an effective algorithm that has logarithmic regret and so on and so forth. So that's the learning side. On the market side, you all probably know about matching markets. On one side, you have buyers. On the other side, you have sellers. On each side, you have a known preference ordering over the other side of the market. So Gale-Shapley algorithm is able to find a best matching in this situation. So this is like interns in hospitals and, and so on and so forth. Beautiful part of microeconomics, Nobel Prizes. But you've got to assume you know the preferences a priori to do all that stuff. What if we don't know the preferences? What if we have to explore to find the preferences? All right. So how do we do that? Well, we have to interact with this market. All right. So here's a little picture where I'm the guy up there picking an arm, and then there's a bear who's also playing the game. And what if both of us pick the same arm? Well, only one of us is going to get the reward. Which one of us gets the reward? Well, in our model, the arm has a preference back on us because both sides of the markets have preferences on the other side of the market. We don't know that preference. Maybe the arm doesn't even know it too. The arm has got to explore. Okay. All right. So there's our setup. Can we have an algorithm that'll work in this setting? And can we get regret bounds? And the answer, yes. So we define a bandit market, which has these agents on one side and arms on the other. We define a natural notion of regret, which is the best regret or the best reward you would have relative to running the Gale-Shapley unknown preferences, if you knew the preferences. Regret relative to that. We define an algorithm which uses Gale-Shapley with upper confidence bounds, okay? As if you knew the preferences, but you use the upper bound of the preferences. And here's our theorem, and I'm about ready to finish, just let my organizers know. So here's a theorem that says that we can get a regret bound in this microeconomic version of a bandit problem. That the regret relative to the oracle Gale-Shapley is logarithmic in n, that's great, but it also has a term in the denominator which has depends on the presence of other agents in the problem. So if Joel is really liking arm 2, and I'm liking arm 2, all right, and I notice that every time Joel picks it, I don't get it, the arm seems to prefer Joel, then I say, oh, damn it, I'd love to get arm 2, but I'm not going to be getting it. So I need to back off and explore the other arms more than I otherwise would have. So I paint a regret there, but I need to do it. It's just real life. And so I'm capturing that regret with that delta term there, which we have in our paper. Okay, I hope that intrigued you a little bit. I think there's lots to do here with all the dynamics coming together with all the game theory. Let me just say this entire talk was really about deterministic dynamical systems. I made that choice just to keep it easy, but in parallel, we've been doing almost all the same kind of work with stochastic processes. In particular, Langevin diffusions are gradient-based diffusions. And so things you could do with gradient-based dynamical systems, you can often do with Langevin with more challenges. And here's a raft of papers from my group, which you'll find on my publication page, doing a lot of the same things I talked about today in the setting of Langevin diffusions. Okay, that is my talk. I am done. So let me just return back to the overall high level here. I think of the current era of machine learning as highly focused on pattern recognition. It's become a commodity. I think it's great. It's really opened up lots of opportunities, lots of new applications. But I think about it a bit like in the early days of chemical engineering, where people were probably building factories and they had no idea really what they were doing, hoping it would work, and there was lots of explosions and lots of people died, and little by little things kind of got worked out. And I kind of think we're doing that in the real world. We're building lots of systems which are not really working very well for human society at large, and we're groping around. So minimally, we got to start to bring in, to be more mature scientists and engineers, the decision-making side. We got to be serious about error bars. We got to be serious about competition. We got to be serious about scarcity, about allocations, about explanations, and so on and so forth. These are all not just thresholdings of neural nets. These are all their own mathematical problems and mathematical theory. At least as far as I'm concerned, this is the area that I'm going to spend the next 10 or 20 years of my life devoted to. So thanks, everybody.
All right. Thank you, Mike. We really appreciate your perspective. For those of you in the audience, we're going to have a short question and answer period. Please enter your questions into the Q&A facility on Zoom, and I'm going to turn it over to Geeta, who will moderate this part of the session. Thank you.
Yes, I mean, there's already a first question from Mengsen Sang, and the question is whether there is an intuitive interpretation of the Bregman-Lagrangian.
Yeah, it's a Lagrangian. That's my best interpretation. Take the h function to be quadratic, and you literally get out 1/2 x dot squared. You get out a kinetic energy. All right, so it really has kind of everything that you have. Now, if you really know your physics, you'll know that you know, Lagrange did his work, and then about 100 years later, people ask, where does that Lagrangian come from? Are there underlying symmetries? Are there underlying principles that led to that Lagrangian? And those eventually emerged. I do not know what those symmetries are here. So I do not have an underlying theory that delivers this Bregman-Hamiltonian or Bregman-Lagrangian. And I think that's super interesting to work on. So if you go to the kind of lower bounds a la Nemirovsky, those were you know, done in a kind of worst case sense. Here's a worst case problem instance which delivers a lower bound. And what I would really like is some axioms that deliver lower bounds in general, and those axioms deliver symmetries to deliver things like this Hamiltonian or Lagrangian. That's for the future. I don't know how to do it. Find it super, super interesting. But other than that, really, it's just a thing which is trying to capture a notion of optimal way to optimize, and we kind of backwards engineered it from all the known accelerated algorithms, including mirror descent, accelerated, and so on. We just found the thing which, like in Lyapunov theory, you find a thing which works, and that's what we did.
Thank you. So the next question is by Lyndon Young. And the question is, what do you mean by provenance?
Oh, thanks for asking that question. Yeah, that's a database person's word. And a lot of people in this field, I think, really don't pay enough attention to the database people. They think of them as just providing the pipes that move the data along. But, you know, the database people are the ones who did like ATM machines, who created the, you know, the banking system that could be online and have, you know, billions of transactions per day and all. And one of the big things they came up with is for every piece of data, you have to have an annotation of where that data came from and how and so on, you know, metadata. And you needed that for auditing purposes, but also just kind of keeping the system working kind of purposes. Now, in machine learning, we don't tend to think about this very much, but we're going to have to. If you think about the medical system, I wrote a little op-ed on AI a couple of years ago, and I had this little example of a medical system problem, which is that a prediction was made in one of my own health situations where it was based on data that turned out to be 10 years out of date. All right. Now, that was not necessarily a problem. Data can be data, but it was a problem because it was done, the data was collected on a different machine than the one that was being used for me. And the change in machine meant that that data was actually giving a huge bias, which gave a wrong prediction, which made us almost have a you know, operation which could have killed somebody. All right. Now, how would you fix that other than me going back and looking up the study, which is what I did? Well, you would have had provenance. You would have had metadata associated with that old data analysis, which says the reason the geneticist is telling you that there might be a problem here is because of a data analysis from 1995. And you better worry about that because the relevance is not so clear because some things have changed. If we had a system support for part of that as our big data science agenda, that every time we have data being used over multiple year spans, not just the data collected today, we got some notion of relevance and provenance accompanying that, then we would start to make better decisions that don't have these possible mismatches between what purpose the data was gathered for, how fresh it is, and so on and so forth. So to me, you know, that's interesting. And that's the kind of contribution a database kind of person can make. But most database people don't think about the uncertainty and the relevance notion in a machine learning sense. They just think about, you know, classical, you know, relevance in a database sense. So it's an open problem and a really important one.
Mm-hmm. Thank you. So there's another question about whether there's a potential connection between game theory, related decision making, and reinforcement learning decision type schemes.
Well, so yes, the answer is yes. It's Hamilton, Jacobi, Bellman theory, right? It's just that, you know, mathematical structure links all these things. Again, I'm going to bash a little bit the kind of current mindset. The current mindset is it's all about neural nets and deep learning. And then if you don't do that, you do reinforcement learning, right? And reinforcement learning is just optimal control theory, folks. It's a particular approach to that. It's a Monte Carlo approach to that, all right? And optimal control theory is also limited. It doesn't do any of the competition. It doesn't do the microeconomic thing. It doesn't do the game theory. It also doesn't do the multiple decision making like we do in statistics and so on and so forth. So it's an okay part to kind of start with some problem thinking about, but it's just very limited too. And really the part of it to me that's particularly interesting is the bandit part. Okay, so it's classically viewed that reinforcement learning is just bandit algorithms, but with time. And even that's not quite right, because in reinforcement learning, you rarely see explicit concern with exploration. Exploration kind of got left behind when people went to reinforcement learning. All right, so I think of reinforcement learning, it's great again that everyone's working on and everything, but there's not that many great applications of it so far. A lot of them bring in ad hoc exploration mechanisms, and the focus just on one decision making or making decisions over time, that's just optimal control. We got to expand our perspective to have multiple decision makers, to have multiple decisions, to have the stochasticity, you know, and the game theory. So, you know, again, with some apologies for getting up on a soapbox here, but I just think we've been way too limited. You know, it's all neural nets or unsupervised learning or reinforcement. That's everything. No, folks, that's just the wrong cut through the space.
Thank you. And then maybe due to time, a last question by René Vidal. You explained how one can go arbitrarily fast in continuous time, but in discrete time, one is limited to 1/k² due to discretization. Is there an intuitive explanation of how the 1/k² limit arises from an analysis of the discretization?
Yeah, there is an intuitive explanation. It has to do with the geometry. And the geometry is that when you have very high curvature, you got to slow down. You can't slow down in the sense of the discretization. If you don't discretize more finely there and slow yourself down, you will lose stability. All right, so the paper that does this the best is another paper with Michael Muehlebach. And so I want to refer again to my publications page. Michael Muehlebach joined me from Switzerland, brought a very strong control theory and dynamical systems background into our world, and has written a couple of beautiful papers, one on lower bounds in continuous time that I alluded to earlier. The other is called something like momentum methods in dynamical systems or something. And it has a very nice intuitive explanation of exactly how the geometry is affecting the discretization.
All right. Well, we're grateful for all of the questions and you taking the time to interact with the audience. I think that's it for today. Our next plenary talk will be next Tuesday, June 16th. We'll hear from Cynthia Dwork at Harvard on her research on privacy. And I'd like everyone to thank Mike one more time, even though we can't hear you.
Thank you, everyone.